our first presentation of the afternoon. Joel Birch of Keysight will be presenting on the testing of MIPI high-speed-PHY standard implementations, challenges, and solutions. Joel will try to keep you awake after that heavy lunch that you had. Joel Birch is a field apps engineer for Keysight Technologies, currently supporting customers here in Northern California. He helps numerous engineers solve measurement challenges for both electrical and functional validation of chipset interfaces such as MIPI M-PHY, D-PHY, C-PHY, also PCI Express, USB, SATA, DDR, and other less common interfaces. So please, let's welcome Joel Birch.
Thank you. Okay, everybody, you got your coffee for your after lunch drowsiness there, I hope? I can't see. All right, so let's see, we'll figure out this little guy right here. Here we go. All right, so what I want to talk about today is a few things with respect to the why we test, what's the purpose of test, what's the benefit of it for you as a customer or as a solution provider of a chipset or an application processor, whatever it is that you're working on. We're going to talk about the MIPI-PHY interfaces that are primarily the high-speed ones. We're going to focus on M-PHY, C-PHY, and D-PHY a little bit. I apologize if that's going to be a lot of review for you, but I don't know what everybody's background is here in the room, so we'll cover a few basics here on that. Then what we're going to do is actually talk about some of the challenges and the solutions for the test environment. On interfaces, there's lots of testing that has to be done, so how do you manage environments where you've got all these different types of tests that you have to perform, whether it's receiver or transmitter test. Multi-lane testing, what are the extra things and extra challenges there and with some possible solutions there and some things that you need to look out for there. When we make electrical measurements, we have to get this signal into our test equipment, so we can do that a number of various ways, either through probes or direct connect. I'm going to make a comparison of those two for you and what some of the differences are going to be for that. And then we're going to kind of shift gears a little bit and talk about some receiver test challenges and what the setup is going to look like, and then also just what other challenges you're going to run into with respect to MIPI in particular, and try to contrast that with some other interfaces that maybe you've worked with in the past. And then we'll just finish up with a quick summary. All right, so the whole idea behind testing is, in particular, as we try to have mature products come to market, is really that we want to make sure that our products are going to meet all the required specifications. We don't want to shortchange ourselves. You want a product that your customers are going to have a lot of confidence in. So you want to be able to say, I meet these specifications. And the testing itself can help reduce your time to market. And what that really means is that early on in your validation process, you can provide feedback to your developers where there are issues in your products in the real-world environment. Hopefully there's a lot of testing that's going on in the pre- and post-simulation environment as well, but when the rubber meets the road, you've got a physical device, and you need to verify that that actually performs as all of your design tools have actually said that they would. And so you really need to do some real physical testing, real physical layer testing, and you want to do that as early on as possible so that you can provide that feedback into the design process. You can find ways of mitigation Maybe it's through tweaking some analog parameter in your PHY and to get your PHYs tuned as well as possible. And of course, you know, the whole objective here is that we want to make sure we have reliable devices. We don't want field returns; those become very, very expensive. And so you want to make sure that not only are you doing this testing early and effectively, but you want to do it in a fashion that is also very repeatable and with, you know, as good an accuracy as you can. And reducing warranty costs, all these things are the standard benefits of doing tests, is bringing a product to market, that, as I said, that's reliable and you know you can have high volume manufacturing for your device. Okay, standards bodies. What's the benefit there? Okay, so MIPI is a standards body. They go through the process of defining standards and developing essentially a name, a brand name, you could say, and you want to protect that. You want to have a good experience for your customers, and so that testing is a benefit to the MIPI name, such that you know, for all the reasons that are listed up above there, you don't want people saying, "Oh, my phone doesn't work because, you know, I got glitches in my display." And well, they might not know that it's a MIPI interface that's failing there, but in the end, that can, at least within the developer community, have an impact on people's perception of what MIPI stands for. Okay, so let's move on. All right, for test and measurement applications, there's different levels of testing. We've got transmitter and receiver conformance testing. We always have a channel, so there may be situations where you need to, and you have to have an understanding of what the channel performance is. So there are impedance and S parameter measurement capabilities for doing that. And you want to have tools for, in your system environment, you want to know that, or have a way to do debug of your system when things aren't quite working right. So debug and bring up tools, scopes, protocol analyzers, those kinds of things are very, very helpful in that environment. And then once again, even, you know, going also more into protocol, there's conformance testing that you can do there, and sometimes device emulation is very, very helpful, especially when you're trying to match up your device to some new piece of silicon and maybe that silicon isn't available yet, or it's not fully functional and operational in all the ways that you need it to be. All right, so if we look at the MIPI product registry, it's a new, I think fairly recently introduced or what's the word I'm looking for? Signed off on, so to speak. I remember seeing an email not too long ago in the last month saying that the product registry program is now in place. I believe it's been going on or being worked on for quite some time. And what this is all about is getting into the mode of having a verifiable method to say, I have a device that meets the standards that have been set for a particular interface. So where that starts is that the MIPI Alliance workgroups define the specification, and from that specification, once that gets ratified, and probably even as the process of ratification is going on or ongoing, there's also a compliance test specification that's being developed that says, okay, I've got this particular spec for high-speed jitter or something like that. And then the question is, well, how do we test that in a fashion that is going to be possible throughout an industry of different chip manufacturers, different test equipment manufacturers, how can we make sure that we're going to get consistent measurement results in different environments such that we have confidence that if you say this passes over here, that I can repeat that measurement and verify that that's really the case. So that's a lot of what the compliance test specifications are about, is to define with enough detail the test methodologies so that you can have consistent and repeatable results. And now that there's a test spec to develop capabilities to, that's where test vendors like Keysight come into play, and they start to develop the test automation that adheres to that compliance test specification, and develop the automation to make those measurements, as I mentioned, in a repeatable and reliable fashion, and then also document that as well. That's a very, very important part of it. So Keysight and other test vendors get involved in developing a document called the method of implementation. And from there, then it's possible to say, okay, this is the way you make your test of this device, whether it's M-PHY or D-PHY or C-PHY. And you can do that yourself if you have made an investment in the test tools, or oftentimes you might want to have an approved test lab or another organization do that testing for you if they've been certified as being capable and having all the right tools to go ahead and make those measurements. So you might have a product, you might not be a MIPI contributor, you might be an adopter company, and you can go to an approved test lab to take your device and get it tested in the same fashion that other companies that might be doing their own self-testing would be doing, okay, and using very, very similar tools. So that once again, the Alliance test work groups get involved here in the approval process of the test labs, and I think there's a sign-off for the contributor self-test capability as well. Once your device is been shown to be tested, then you can have that product listed on the product registry. This is a process that has been developed and been in place for many interface standards in the market today, over and over. And I'm sure many of you are familiar with this being in place for interfaces like USB and PCI Express and SATA. So this is actually not a new kind of thing, but putting all the pieces together takes a little bit of work. Okay, let's take a quick look at the MIPI interfaces here. So let's see if I can try this laser pointer here. So there's really three primary high-speed interfaces. We have D-PHY and C-PHY is right there, okay? And then M-PHY, you'll notice in the red bullets over here and these ones here. These are the high-speed interfaces that are the more challenging ones to validate in MIPI. MIPI also has some much lower speed interfaces. We're not going to be talking about those today. But if you look at the partition here, primarily you see D-PHY and C-PHY for camera and display interfaces. And then M-PHY actually is specified as the physical layer for a lot of other different interfaces. The primary one being UFS right here, where M-PHY sits below the UniPro protocol stack. So let's go ahead and dive into this a little bit more here. I think I mentioned that, camera and display, and M-PHY being spread across all these other interfaces here. UniPro, oops, let's see, press that too many times there. There we go. UniPro being the one that's most prevalent for M-PHY. All right, so if we look at an M-PHY example, M-PHY is a a differential interface. So we have our M-PHY transmitter talking over a differential line to its receiver here. It is a differential AP10B encoded interface here. For many interfaces, and I don't think it's for all, actually is that, well, it might be for all. We also have a receive direction as well for M-PHY. And so we have both a transmitter and a receive function in the port here. There is a high speed and a low speed mode for M-PHY. When we're in the low speed mode, we have either a pulse width modulation type of encoding of our data, or we have basically a low speed NRZ interface, which is called the sys interface. And so because we have a serial encoded encoding here, AP10B encoded interface, the clock recovery is an important function here that takes place in the receiver. Okay? All right, one thing also I think that's worth noting is that M-PHY has, for a specific implementation, you always have, for the high speed and the low speed modes, you always have the same high and low voltages. It's always NRZ encoded, or it's always just logic 1 and logic 0 at specified voltages. There is both a high and a low voltage swing operation capability, but that's kind of essentially assigned at the time that the system comes up or designed into the system to be operating in either a low amplitude or a high amplitude mode. And it's terminated at 100 ohms differential. So in order to meet the requirements of different types of applications, the M-PHY specification specifies different data rates, initially starting out here in the gigabit range right here. And I think there was a talk earlier about how where the M came from for M-PHY. That's standard for 1,000, meaning 1,000 bits per second. So that's this gear 1, which is what it's referred to, starts at these lower speeds, and then subsequent gears essentially double, or pretty much close to double the data rates as they go up into these higher data rates. So this is one way that you can get higher throughput on M-PHY. Another way is that you can also have multi-lane interfaces as well. Okay, so here's our high-speed mode right here. Almost always it's got a resistive termination here. There is an optional non-terminated mode for those, but I don't think that gets used that much in the high-speed modes. And then for our low-speed PWM, the data rates fall into these different categories here of data ranges, and you can mix and match the low-speed gears with different high-speed gears. So you don't have to support all of these, and let's say you supported a gear 3 here, that doesn't imply that you support gear 3 over there. And where mostly we see PWM type of operation here for M-PHY versus the type 2 sys interface here, which is used, I think, only for DigRF right now. Okay, let's see what we can find in here that's relevant. Okay, so our signaling is always differential in-band signaling. I think I mentioned that already. Same amplitude. These properties lead themselves to specific selections of test equipment. The fact that we have only the 2 signaling levels and we have NRZ signaling allows M-PHY to be tested primarily with a Birch when we're talking about receiver test. And there's going to be implications for some of the other interfaces about how we what kind of test equipment we have to choose for the other interfaces because they're multi-level signaling. So now if we transition here to D-PHY and look at this, what is characteristic about D-PHY is that we actually have two different transmitters, essentially, and two receivers. We have a high-speed transmitter and I think it's that guy right there is our low-speed transmitter right there. So in D-PHY and C-PHY, what is relevant here from a test perspective is that we now have two different voltage levels. We have our high-speed signaling levels, and then we have our low-power signaling levels. And that has an impact both on measurements that we might make on our transmitter as well as on our receiver, and how we make those measurements and what kind of test equipment we're going to choose for that. So we have 1 volt unterminated large amplitude signaling for LP mode, and here we see the 200 millivolts right here. Okay. I don't have a timer here, so I'm not sure. It says overtime. 20 minutes. Okay, I got to get going here. Thank you. All right, same thing for C-PHY. Similar kind of setup here that we have with respect to the signaling levels. So that's going to impact our test tool selection here. Okay, we're looking at D-PHY again here. The relevant thing is we've got a source synchronous clock and 1 or more data lanes here. And so for each one of these data lanes, we're going to have some level of testing that we're going to have to do. And nice thing about D-PHY from a protocol perspective is that the data rate is completely agile. You don't have these fixed speeds that you have in M-PHY. And so, you know, as a system developer, you can tune that data rate to what's appropriate for the application. Okay? Now, on the receiver testing, there's a couple of different variations on that, and I think we're going to be going into that here in a minute here. And that's something that's changing over time as we go to higher speed gears. Okay, once again, C-PHY, this is actually single-ended signaling here. We have a three-wire interface, and completely agile data rate once again. And we're going to do our receiver testing through an eye closure mechanism as well. All right, let's take a look at some of the challenges that you're going to run into as you start to go into the lab and test your devices. And we'll start here with this category of huge list of tests. What you're going to probably need or want to do to be efficient in your daily workflow is to at some point either purchase or develop your own test automation. There's just a lot of tests that you're going to want to perform or going to need to perform such that you want to have the ability to do that in an efficient manner. You want to have the ability to test at different data rates, different termination types. You want to have the flexibility to choose which tests you're going to run. So you may want to go through a full suite of tests to get an audit of your device. And then later on, as you find those tests that are only maybe passing marginally or perhaps failing, you're going to want to go back and repeat those tests. So you want to have that flexibility to choose how your test environment operates. There's a chance that you might have to make physical changes to your test automation setup. It might be different probing. It might be that in some cases you need a channel, in some cases you test without a channel. So you need a way to try to help out in those circumstances as much as possible. Let's get back here. And then lastly, you may not care as much about it as your management chain, but you need to at some point report some results about what's going on with the device. So you want to have a way to get at the data that you collected as easily as possible. Also, one thing that's really very, very relevant with MIPI in particular is that there are a lot of cases where your device, you might need to have your device put into special test modes. And so you want to have, if you can, put your device into these modes through your test automation flow as well. And so if your test software can integrate in with your device control interface, then that's very, very beneficial. So here's an example of a test automation application. This one happens to be from Keysight. No surprise there. But we have the ability to select different gears. You can document things about what the device under test that you're testing here. Test selection right here, and then test results are generated for you. And all that's done essentially with the press of a few button clicks. I'm not telling you to go out and buy our stuff, but I just want you to think about some of the capabilities that you might want to have either in your own in-house developed test flow or when you start looking at third-party applications. These are some things that you might want to consider. All right, so let's talk about multi-lane testing. So let's say you've got a D-PHY interface, a 4-lane D-PHY interface, and you tested lane 0. Okay, you're all done. Well, congratulations. Not exactly. You've got 3 more lanes you've got to test. So every time that you have a new test or a new lane, or a new configuration, that potentially opens up an opportunity for doing things like having a switch is an example. And so I think we're going to be showing an example of that here in just a second. But let's see what else this is implying here. So really what we're talking about is when we get this big list, whenever we have multiple lanes, we're having to multiply that out by whatever number of lanes that we might be having. So we're talking about additional test time. Either you or somebody else, I'll say, is in the case of a multi-lane device, you're going to have to make physical changes to probing. So after tests run for an hour, you need to come back in the lab and do that. Or you can potentially have another scope testing another device. That's where you have the issue of expensive test equipment. And there are other ways. So let's take a look at a switch environment right here. So here's an example right here. We've got a multi-lane device here, cabling going out to a switch right here. And our test automation software, we have told it that we've got this multi-lane device and that we are wanting to test one lane after another. And where this saves you a lot of time is that, first of all, you don't have you don't have wear and tear on your connectors like you would when you're having to move things back and forth all the time. That's a consideration to think about. As if you continually have to do that, not only is there a lot of time involved, but you're also deteriorating your test connectors, and at some point that's going to have an actual real and measurable impact in the results that you get. The big savings is in time. Is you can press the button one time and let all the software take care of all that for you. Now, here's the problem though, is that we've just added a whole bunch of cabling here to our test environment. So now what we have to think about is that we have a high-speed signal going across, hopefully not that lossy, but there is some loss in these cables, okay? And we're going through a switch that has some additional loss. We've essentially extended the length from our DUT to our test environment significantly, and we now have some loss that we have to compensate for. So you can do that in today's modern oscilloscopes, they actually have de-embedding capability, and that helps to compensate for this additional loss. Now what you want to do, though, is make sure that you've measured that so you know how much loss to back out from your measurement. There's also some other considerations when you think about this, and that is no matter how good this de-embedding or loss removal software is, you're fighting a losing battle when you make these connections very, very long. And that is because as you have more and more loss, the removal is essentially applying an inverse filter. It's basically applying you can think of it as a high-pass filter, and your high-frequency components are getting boosted, but not only to compensate for the loss here, but also your scope, high-frequency signal components, the noise that is inherent in every measurement instrument also gets boosted as well. And at some point, that noise, if we have enough compensation, becomes very significant, and you start to have some impairments from this de-embedding process itself. So what you really want to try to do is still to use good cables, low-loss cables, have a low-loss switch. You want to try to keep these cables as short as possible, and that's going to be beneficial to you in your test environment. Okay, let's move on to probing and termination. The high-speed interfaces are generally terminated 100 ohm differential. In an environment where we're trying to make that measurement, say for M-PHY gear 1 as an example, or D-PHY, we would have a dynamic resistive termination board, the RTB, and you can solder down high impedance probes there and make your measurements with the scope this way. Another method is to do the same, but actually have just a fixed 100 ohm termination on here and kind of, well, basically remove it for the unterminated mode. Now, obviously, that doesn't work for a dynamic environment. It's going to impact you can't really use this for LP tests right here because it's expecting an unterminated interface there. But there are some benefits to doing this in that you don't have a device that is actively switching termination and potentially introducing some noise into your measurement environment. Okay, so now another option is that you can go direct into your scope. The downside of that is you have 50 ohm to ground terminations. You no longer have your 100 ohm differential termination there. But there actually is a benefit here that you can see when you're in high-speed mode looking at an eye. Probes, active probes from us and from any scope vendor, they introduce noise into your measurement environment. And in particular, that comes from the probe attenuation ratio. Any signal that goes, say if we have a 3-to-1 probe, the signal at the probe tip is going to be 3 times smaller at the input into the scope. So now the scope has to compensate for that. That gets mixed with the scope noise and gets amplified to get back up to the correct amplitude. And so now what we're doing is essentially adding noise into our measurement here. So we see here some additional eye closure. There's 182 picoseconds there. Am I looking at the right thing? No, I'm sorry, eye height right there. 72 millivolts right there. And over here we have 94 millivolts. So we actually have a lower noise measurement over here when we don't use an active probe. So the moral of the story there is to try to use a probe with as low attenuation ratio as possible. And one way to do that is to still, you can actually do the measurement by, and maintain that 100 ohm differential termination by actually terminating not into 50 ohms, but into some non-ground voltage. And I'm not going to go through the math here. It's very simple math, but I'm running out of time here, I suspect. And the idea here is that you can still maintain the behavior of a 100 ohm differential termination, meaning low or no current flow, and still have a direct connecting to your scope there. And so here's an example right here. Now what we've done is with this particular active termination probe here, we have 88 millivolts versus 94. So we've actually improved our measurement results from the previous example where we had the active probe in place. Okay, let's finish up here. Got two more things to talk about. Receiver test calibration. The calibration environment for gears 1 and 2, or gears 1 through 3 that is, actually is going through from a test generator like a Birch, going through a conformance channel here, and then the replica trace, and we have our calibration plane right here. And so once calibration is done here, then we change our connection to do our testing, our receiver testing. So what we're doing is we're developing a stress die through this calibration path right here to this plane. And then we can know that we're actually testing with that same stress die to the exact same location going into our device under test right there. When we look at gear 4, there's an added complication here, and that is that now we really want to, there's an equalizer in place for gear 4, and so what we want to be able to do is to have our calibration done after that equalizer. So what we're going to do is a similar process here, and where we're going to get the equalization done is in the test tool itself. So here's the eye that might be present right there before the equalizer, essentially right there. And then what we do is with the oscilloscope capabilities, we add in CTLE and DFE equalization to open up the eye, and we have our compliance eye specification right there that we can identify, and then we know at a particular settings of impairments here on our Birch, this is what we're going to get at the plane after the reference equalizer right there. And here's an example of a test setup that implements this exact setup here. You'll notice here that we actually do not have an ISI channel here. And the reason for that is that in this particular Birch, we can actually emulate ISI through the implementation of FIR filters at the front end of the outputs of the Birch. And so that has a lot of nice advantages in that you don't have to match up different trace lengths externally, and you can just dial in essentially just through user interface or programmatically how much loss you want at a particular frequency. And so you can nicely trim the conformance channel, ISI conformance channel to the loss that you need, including all your cabling loss as well. All right, last subject here is talking about some of the challenges for receiver testing in the MIPI environment, and that is, well, we want to introduce a stressed eye, and we want to send in a known pattern and count errors. And MIPI doesn't really specify very well that you have to have testability in your device. And so a lot of devices don't have error counters, they don't have a loopback path, and that raises a lot of challenges for receiver test is the bottom line. So here's just a quick survey. Here you see that for DigiRF, this is that and Unipro 1.4, these are the only two that are specifying that there's a test mode. For DigiRF, it's a loopback path that you have to have, and for Unipro, there is a specified error counter. But some of these other standards, basically you're on your own. It's up to you in your silicon, design to implement testability. So that could be in the form of a loopback path or an error counter. And those are the two traditional ways of doing that. So fundamentally, the bottom line for receiver test for MIPI is you're likely going to be in this environment right here where there's going to be a lot of consideration that you're going to have to make for how you get that receiver test done, and it may not be the same solution in every case because of the implementations of testability that you might have in your silicon. There's an example out on the test floor that I'd encourage you to come see with our partners D-PHY, and I'm not going to go into any detail on this right now, but you can actually come out and see this running out there in the hall there. That's all I have to talk about. Here's some reference material if you want to find additional resources, and please come visit us. Any questions?
Any questions for Joel?
All right, thank you. Let's give that to you.